Dear students, hello. We are proceed with our lectures, uh, and it is now all time we have considered the so-called linear electrical circuits. It is circuits which parameters do not depend on levels of applied voltages and on levels of flowing currents. But this part of this course, one of the last parts, it's about steady-state processes in nonlinear electric circuits. Let's consider elements which parameters depends or parameter depend on the level of applied electromagnetic field parameters. Any electric circuit is considered as nonlinear if it includes at least one nonlinear element. And nonlinear element is an element in which current and voltage have nonlinear dependence on each other. Processes in nonlinear electric circuits described by nonlinear algebraic or differential high-order equations, and it is not possible now to use the superposition principle, and this principle is not applicable to the nonlinear circuits. Nonlinear resistance is designated in such a way. You see this additional part presented here, and it means that it designates that this resistance has nonlinear connection between applied voltage and current which will flow through this resistance. You see, it is not linear, which was equal earlier. It was equal to just to R, to resistance, and here it is equal to Ru. Here, this volt-ampere characteristics of such a resistor is nonlinear. You can apply such voltage, for instance, and got such current. And if you applied such voltage, you got such current. Here you see further for this part of this curve, further amplification of voltage, a slight amplification of voltage will cause very significant amplification of currents. Okay. Then nonlinear capacitances, they are designated in such a way with these additional linears when it is depicted. Cu, here we have dependence on electric displacement D from applied electric field strength E. Such dependencies, you see, it is here, and here we've also seen, not like here, just non-ambiguous dependence between U and I, but here we have more complicated dependence, the so-called curve in which D depends on I, not directly. It will depend on the history of this particular sample, how it was subjected to applied electric field with intensity E. Such dependencies are characteristic for instance, such material as ferroelectric materials. These materials have dependence of this dependence of C or dependence of D from level of applied potential U or connected with it electric field intensity E. And here is nonlinear inductance. It is depicted in such a way. Yes, and we have here dependence of magnetic induction from applied magnetic field intensity. And here we've seen that at first it go by such a curve, then it go by a curve here in this way, and when we when applied magnetic field strength is lessening up to negative values, and then it is it go by such curves, and it is really complicated case of nonlinear elements. And these characteristics of nonlinear resistance, capacitance, or inductance can be obtained experimentally, and such experimental dependencies can be approximated by analytical or numerical expressions. Such dependencies are called hysteretic dependencies, because we have not like here an ambiguous connection between these parameters, but we have here some curves which depend on the history, as I have told you, of the history of applied electric or magnetic field intensities. So let's consider influence of saturation and hysteresis effects on currents or inductance with ferromagnetic core. We will consider only in this course we will consider only hysteretic dependencies of B over H, or hysteretic dependencies of inductance, these nonlinear inductances, because it is connected with usage of such elements, I mean ferromagnetic, in transformers. So, sorry. Relative magnetic permeability, mu, in ferromagnetic cores of transformers is have not constant volume. Magnetic flux density B related to magnetic field strength H, or magnetic field intensity, with such a dependence B equal to mu 0 H. I have told you about such dependencies in the end of our previous semester. It was course of some part connected with basics on which this course is based. So we have here mu 0 H, mu 0 equal to 4 multiplied by P multiplied by 10 power minus 7 Henry per meter. It's a constant. Mu is relative magnetic permeability, which can depend on level of applied magnetic field intensity, and actually as B equal to mu 0 multiplied by H, so this curve, from this curve we can get dependence of mu from H. And magnetic flux density B linked to magnetic flux, it may be called to magnetic flux F through the core cross section S of steel, in such a way for ferromagnetic circuits. It's for any circuits, but for ferromagnetic circuits, this dependence will be nonlinear. So F equal to B multiplied by S. S, it's cross section of the considered medium. And we can also write down equation which connect current and magnetic field intensity. It may be done with in accordance with Ampere's law. We do know that current flowing through inductor and magnetic field intensity H can be connected in such an equation. IW equal to H multiplied by LA. Here, W is number of turns of winding, LA its length of median magnetic line in the magnetic circuits, I current through this winding, and H is magnetic field intensity. It is this Ampere's law should be known to you from the course of physics, and I have mentioned it also as I have taught in the end of previous semester. And so we can write down with the help of these equations, we can write down connection between flux, magnetic flux F, and current through coil I, in similar dependence as B and H here are connected with each other. And such a dependence, F from I will represent also curve identical to this hysteresis curve. In the magnetical soft steels, which as a rule used as a magnetic cores of electric machines and apparatus to avoid these hysteresis losses, we will consider that this loop, such a loop, tends to loop without hysteresis. We will not take into account this as this width of this curve is relatively small. We will not consider these losses on hysteresis. And for instance, permanent magnets with this hysteresis loop will be rather wide, and it cannot be considered that it is just dependence like this without these hysteresis losses. So at first we will consider the so-called magnetically soft steels with hysteresis losses, in which hysteresis losses may be neglected. And let's consider circuits with such circuits which are used in electric machine and electrical and transformers. Let's proceed with this material in the next lecture, and please listen it because it might be useful for you in your future engineering career. Bye bye for now.